In this lesson, we'll be going over the Routh stability criterion, which will include a little bit of background of the Routh criterion, closed loop function, characteristic equation, and the Routh table. And a majority of this can be found in your FE handbook. So what is the Routh criterion? Well, the official definition is the Routh criterion is the stability of a common unity feedback signal loop linear system model and can be investigated by referring to the closed loop transfer function. So in the picture below that official definition is the diagram of a closed loop transfer function. And we'll go over that a little bit more as far as how to take a transfer function and make it closed loop and figuring out the equation for it. Okay, the stability of that system depends on the location of the poles and zeros in that complex S-plane. And again, I'll go a little bit more in the examples. The variables of that closed loop transfer function are the roots and expressed in the characteristic function. Now, as I said earlier, the characteristic equation as well as the closed loop function, all those are in your FE handbook. So if you need to refer to that material, just pull out that FE handbook. Now, some of your reference material may lump together the Routh test as well as the Hurwitz test, which is known as the Routh-Hurwitz criterion. All right, so let's go over the overall steps of how to go through the Routh criterion. First step, you establish the closed loop transfer function. You determine the poles and present them in the characteristic equation. Then you utilize that characteristic equation and populate the Routh table. So let's kick off by going over the first step, your closed loop function. Now be aware some of your reference material may refer to the closed loop control systems as feedback control systems. And based on the polarity sign, we'll determine if the system is negative feedback or positive feedback. Now we went over this a little bit in the block diagrams for control systems, but it's going to be the same concept here. Now, the very easy way to determine your closed loop functions is to add or subtract the numerator to the denominator. Now I have an example at the bottom here where it's k over s plus 1, and that's your open loop function. But as soon as I have a negative feedback, all I did was take my numerator k and add it to my denominator, and that created my closed loop function. And we'll go over this a little bit more in the example problems. All right, step 2, create your characteristic equation. Now the denominator, which is your roots, determines the characteristic equation of the system. So the equation below, we have k over your denominator, and that is your roots or your poles, and we derive from that your characteristic equation. So a very simple example at the bottom, I'm just using the denominator to determine that. And it's very simple. Again, I'll go over this more in detail in the practice problems, but this is probably the easiest step out of all of them. All right, your third and final step, the Routh table. This is where the meat and potatoes of this lesson comes in. All the roots of the characteristic equation have negative real parts if and only if the elements of the first column of the Routh table have the same sign. So I have the Routh table below with all the equations needed to populate it. But we're going to mostly focus on that first column. And we're going to look at the constants of that first column. And if they're all negative or all positive, then the system would be stable. And you're going to get a full understanding of how this works in the examples which we're going to go over next. All right, let's jump right in with a relatively easy one. This one, we're not going to go too deep in the weeds on the first go around. We're just going to go over the Routh table and how to fill it out. Now for this one, I already provided the characteristic equation. This is already pre-filled out and already matches this guy right here. So all we want to know is if this function is stable. So we're going to go over populating the table and solving the table with this function. All right, let's jump right in. So let me go ahead and create a table, or one that looks somewhat decent. So it's S3, we're going to start with that guy, S2, S1, and then S of 0. So in a sense, I'm going to try to mimic this guy right here. So let's start populating this. A and N, that's going to be your first guy right there. It's going to be your first variable. So as long as you have these in numerical order, in other words, cube, S square, S, and then S to 0, as long as you have them in that order, you could pretty much plug and chug it the same way. So the first one is going to be S to the 3, which is, and that's a 1 there. If there's nothing there, it's 1 times S to the 3. So the first one is 1. Now we need to go AN negative 2, which is that guy. So it's the first and third for the characteristic equation. First and third. So that would be a 5. And since there's no 4, that's a 0. Okay, let's go to the next row. Next row is, we want A and N negative 1. A and N, subtract 1. So it's going to be our second guy, which is 10S, which is 10. So same thing, a and n negative 3, so we have negative 2. This one's going to be to the negative 3. So that one right there is going to be 48. And then, of course, there's no 5. Again, the characteristic equation is not that long. I don't have a function that long. I'm trying to keep this under 6 minutes. So this one's going to be 0. Now, this is where these equations come in. The third row has b of a. So b of a, and again, this is in your FE handbook, so if you need these equations, they're in there. It's going to be this guy right here. We're going to start plugging and chugging. So a and n negative 1 is going to be this guy right there. It's going to be 10 times, and then a and n negative 2, which is 5. And that's going to be subtracting 1 times 48. Because this one's 1, that one's 48. Okay? And that's going to be over a/n negative 1. So it's going to be our second variable, which is 10. So if I bring this down here, it's going to look something like this. 50. 10 times 5 is 50. Minus 1 times 48, which is 48 over 10. So simplifying that down one more time, it's going to be 2 over 10, which is going to give us a simplified answer of 0.2. So right there, it's 0.2. Okay? Next one's going to be B2. Probably thinking, why don't I just go ahead and fill out this one, why don't I fill out the first column and leave the other ones alone? Unfortunately, like for example, C1, it relies on B2. So you have to fill out B2 and then go on to the next row. So you have to fill out each row one at a time. All right, so let's determine B2. Let me clean this up. B2, same thing, a negative 1, which is 10 times, and then it's to the times the fourth one, which is 0. That's going to be negative, and it's going to be a and n, which is 1, times to the fifth one. Again, since the characteristic equation isn't that long, it's actually very small, a lot of these are going to be 0. So that's going to be over, and that's a and n, negative 1, so it's going to be over 10 again. One's pretty easy. 10 times 0 is 0, 1 times 0 is 0, so it's going to be 0 over 10, giving us 0. So that one's going to be 0. And then, of course, B3, there isn't a B3 for this particular equation. You can keep going with these, but since this is a small function, we don't need to go that far in the weeds. All right, last row, C1. So let me clean this up. All right, C1. So it's a negative 3, which is this guy right here, which is our last one, number 48. I'll tell you what, just so you see what I'm doing. So that's a of n, that's a of n negative 1, that's a of n negative 2, that's a of n negative 3. So you can kind of see where I'm getting these from. So when you actually do the test, go ahead and write it down right there next to it, and that way you can just start plugging and chugging it really quick. All right, then we're going to times B1 times B1. B1 is 0.2, so it's times 0.2 minus a and m1, which is 10, times B2. Well, B2 was 0, so that's times 0. And that's over B1, which is 0.2. So if we plug and chug this down a little bit, it's going to be 0.6 minus 0, 10 times 0 is 0, over 0.2, which C1 would equal 48. Pretty easy plug and chug. So that's 48. I could go ahead and answer C2, but there's no point. I have what I need, which is our first column right here. So I need to determine, is this function stable? Well, every single constant in this first column is positive. Since that fits under the rule book, is stable. Jump right in of how to populate this table and how to quickly determine if it's stable. All right, let's do another example. All right, for our second equation, we're going to determine if this function is also stable, but we have a little bit more in the mix that we need to do this time. This one, we have a closed loop transfer function. Let's go through the steps. This one, we need to determine the closed loop function, determine the characteristic equation, and then populate our Routh table. First step, closed loop function. Well, let's go ahead and write out an open loop function, which is this guy right here. It's 12 over s to the 3 minus 4s squared plus 8s. Okay? Now, we talked about in the PowerPoint, a very easy way to make this a closed loop function is pay attention to polarity, and all you have to do is add the numerator to the denominator based on that polarity. So, this is open. Now we want to do closed. Well, since that's a negative feedback, all I have to do is add my numerator to my denominator. So it's going to be 12 over s cubed minus 4s squared plus 8s, and then it's going to be plus 12. That's all I did. Very quick and easy way to make this a closed loop function. There, that's step 1 complete. Now, we need to determine our characteristic equation based off this equation. Well, like we talked about, the characteristic equation, all it is your denominator. And since this is already in numerical order, all we have to do is plug that into that, and that's all, and that's your characteristic equation. So, in other words, I'll write it up here, that way I have room. Your characteristic equation comes out to be s3 minus 4s squared plus 8s plus 12. And that's all it is. And I'll tell you what, I'll make it easy on us. A of n negative 1, A of n negative 2, A of n negative 3. That way when I plug and chug it in the table, it's much easier to follow. See how I did that? I know I did it very quickly, but since it's a negative feedback, I was able to add my numerator to my denominator. This is very similar to how you solve block diagram control systems like we did in the previous lesson. All right, so we already did step 1. There's step 2, characteristic equation. 3, let's go ahead and populate our Routh table. Let's only clean this up. All right, I'm going to create a table. I know I have the best handwriting, don't I? So I have S3, S2, S1, S0. All right, filling out the table. First guy right there, A of n is 1. Number 2, 8. 3, well, there's no 4, so that's 0. Okay, next row. A of n negative 1, negative 4, negative 4. Okay. Next is A and n 3, so that's 12. And then we don't have a 5, so that's a 0. Okay. Here's where it gets fun with our equations. Third row, B of 1. So same thing as last time. I'm going to take the equations and then do A of n1, which is negative 4, times A of n2, which is 8, minus A of n, which is 1, times, and this is A and n3, which is 12, over A and n1, which is negative 4. Simplify this down. It's going to be negative 32 minus 12 over negative 4. So let's simplify that down a little bit more. So I got negative 44 over negative 4. So B1 equals 11. Okay? Well, that's not a good sign already. So now we can find B2. Let me clean this up. B2. So again, we're going to follow this equation. A1, negative 4. A4 doesn't exist, so it's times 0, minus 1 times 0 over A1, which is negative 4. Well, we have negative 4 times 0, 1 times 0, so B2, just to save some time, it's 0. All right, and let's go down to the next row. Let's up one more time. C1, so C1 equals A and n3, so it's 12 times B1, well, B1's 11, minus 1, which is negative 4, times B2, well, B2 is 0, over, and this is B1, B1's 11. So we have 132 over 11, which is actually really simple. All it is C1 equals 12. And of course, we don't care about the rest. The first column, unfortunately, we have a negative 4 there with 3 positive numbers. Mismatch of signs here, which means, rule of thumb, this system is unstable. -4 is what throws you off. If it was -4 wasn't there and it was a +4, would have been a stable system. Do one more problem. All right, last example. Now you've noticed I'm building you up little by little of how to ease into these questions. For this one, we're going to find the system stability. Now this one, we have a little bit more work to do as far as finding your open loop function as well as your closed loop function, and then characteristic equation, and then your Routh table. Let's see if we can simplify this block diagram right here. Well, following just the regular block diagram rules, anytime it's in this formation right here, one after another or cascading, you multiply them together. For example, it's going to be k plus 10 times 1 over s plus 10 times 1 over s plus 8. So if you multiply all those together, and again, we're just trying to find our open loop function right now, it's going to be k plus 10 over s plus 10 times s plus 8. All I did was simplify this one open loop function right here into a single box. Hence, it's going to look something like this. K plus 10 over s plus 10 times s plus 8, and then I'm taking it back to a negative feedback. Okay, that's all I'm doing. I'm just simplifying it down. Let me get rid of this. That way we're done with that visual. We talked about our little rule of thumb. All you have to do is take your numerator and add it to your denominator. So all I'm going to do is take k plus 10 over s plus 10 times s plus 8 plus k plus 10. So all I do is take my numerator and add it to the denominator. That's all I did. Well, now we should be able to simplify this down and make it look like a characteristic equation, because right now it doesn't even mimic that yet. So now we need to go ahead and see if we can multiply this together and make it look good. So all I'm going to do is I'm going to multiply these two together right here. That's all I'm going to do. So s times s squared, plus s times 8, s8, plus 10 times s, s10, plus 10 times 8, 80. And then I'm going to put plus, and I'll bring it down here real quick, k plus 10. So right now, this is our characteristic equation right here, this big guy right here. Tell you what, let me see if I can simplify this down one more time. So I'm going to move this over and simplify it down one more time. So all I did was k plus 10 over, and that's s squared, plus s8 plus s10 is 18s, plus 80 plus k plus 10. Well, I have an 80 and I have a 10, so that should be easy to add those together. Makes 90. So the complete and final equation is going to look like this. S squared plus 18s plus 90 plus k. Okay, so right there, that's our simplified function right there. So all I did was just take this block diagram and create a very simple equation right here, or a simple transfer function. Now we could take this function and start plugging it into our characteristic equation and then to our Routh table. So let me go ahead and move this up here. Now, as we talked about, the denominator is the characteristic equation. So this is a and n minus 1, a and n minus 2. Now this right here, these two together, is considered a and n negative 2. So just be aware these two are actually considered its own constant or its own variable. We could populate a Routh table since we have our characteristic equation. So let me go and draw it. Now this one's actually a little simpler. It's going to have less rows. S2, S1, S0. Same thing as last time. S2, first and third one, which is 190 plus k. Pretty simple. Second row is going to be a and n minus 1, which is 18. And then your third one, which is 0. There is no third one. Last row It's going to be B1, which is plug and chug in our equation. 1, so it's 18 times AN2, which is 90 plus K, minus 1 times 0. Since we have AN 1, and that AN 3 does not exist, so it's 0. So it's over AN 1, which is 18. So if you multiply this together, B1 equals 18 times 90 is 1620 plus 18K, and then it's over 18. So all you do is kind of undo what you just did here. So it's divided by 18 is going to be 90 plus K. 1 equals 90 plus K. All right, and B2 requires A in -4, A in -5. No bother, that's going to be a 0. All right, so we have our first column available. So our first column is all positive numbers. However, we have K right there. So just because all these are positive doesn't mean that's it. You have to find the system stability. Well, we need this whole column to stay positive. And the only way this is going to stay positive is as long as K does not exceed -90. In other words, 90 plus K equals 0. So as long as K doesn't go to -91, then your system is stable, which means K must be greater than -90. Because right now, K can go all the way up to 1,000, doesn't matter. It's in the negative direction is what we care about. So we need K to always be greater than -90, because as soon as you hit, for example, -91, that means this number right here becomes -1, which means your system's unstable. So your system stability, K must be greater than -90. So all I did was just take this guy, move him over here, and move a variable to the other side of the equal sign, becomes a negative. So that's how we have -90, and K must be greater than -90. So our answer for this one is K must be greater than -90 for your system stability. Hopefully I gave you enough information to be dangerous and I didn't confuse you too much. Any more questions, feel free to let me know, and I hope you all have a good day.